Hello, everyone. Today, our group is going to present a project that we have done research on about LEO satellite networkings, which LEO stands for Lower Earth Orbit. And today we are going to report several aspects of this project, which is first, the structure of the LEO network, operation of the LEO network, performance of the LEO network, challenges and limitations, and in the end, impacts of this networking system in global manner. And let's dive into the LEO satellites. And our team member, I am Wen Yijie, which is going to talk about the structure of LEO networks. Luke is going to talk about the operation of networks and some aspects of performance comparison. And Adam will talk about major challenges and limitations of LEO network. And Ryan is going to talk about global impact of LEO in socioeconomic ways to give a broader picture. And now we are going to talk about the structure of the LEO networks. And for my part, I will introduce the overall structure of LEO satellite networks. Lower Earth orbit systems like Starlink and OneWeb, in my research, two of examples, work very differently from traditional geostationary satellites. Instead of placing one large satellite 36,000 kilometers above the Earth, LEO networks deploy thousands of smaller satellites in multiple orbital planes, typically around 1,100 kilometers in altitude. Each plane contains roughly 50 satellites, and they orbit the Earth about 1.8 hours. Because they move so quickly, and the coverage is achieved not by one satellite staying in the place, but by a coordinated handoff from one satellite to the next, creating a continuous global network. These systems rely heavily on the frequency organization. For user connection, Starlink used Ku-band, which provides wide area coverage for home terminals. For backhaul to the internet backbone, it uses Ka-band, Ka-band. This band supports high-capacity links between satellites and ground gateways. Users' terminals on the ground, usually around 30 to 75 centimeters in size, use electronic beam steering to track fast-moving satellites. And meanwhile, gateway stations with larger antennas provide long-distance high-throughout links to the core network. And here we can see through this picture, each satellite used to have an average 40.46 that when this is the optimum range of transmitting the signals, and this is usually being integrated through the Ku-band. And historically, ideas like NASA ellipsoid system proposed as early as 1900s already explored this kind of ideologies and ideas, constellations, and from these kind of range of degrees, they can also transmit this information throughout each other in the Ku-band system. And although the project was never launched, its concept still stays and implemented by the latter SpaceX and the examples I gave. In summary, the structure of LEO networks combine orbital geometry, frequency planning, user terminals, gateways, and inter-satellites into one integrated system. And as technology evolves, future LEO networks are expected to incorporate with AI-based routings, which is yet coming, multi-layer constellations, and even 6G terahertz communication, as one of my report has written, and it further expanding the global connectivity. With all of this said, now that we have established the overall structure of the LEO constellations, how the satellites' orbits and frequencies are organized, we can move on how the system actually works in real time. And Luke will explain the operational side of LEO networks and show how these satellites coordinates to deliver continuous global connectivity.
So the operation of LEO networks primarily operate through three main components, which are the space segment, the ground segment, and the user segment. So the space segment involves the satellite constellation itself. LEO satellites orbit much closer to Earth, around 300 to 2,000 kilometers, which means they move very quickly, and they complete an orbit in about 90 to 120 minutes. Because each satellite only covers an area for a short time, LEO systems use hundreds or thousands of satellites in coordinated orbital planes. As one satellite moves out of range, another moves in, which creates seamless coverage. And the satellites also use inter-satellite links, which are usually laser connections, which pass data between each other. And that helps reduce latency and allows information to travel through space instead of constantly going back to ground stations. So the ground segment includes the infrastructure that connects the satellites to the rest of the internet. Gateway stations receive data from satellites and send it into the core network. And they also send data back up through uplinks. The core network handles things like routing, authentication, and traffic management. And control centers monitor all the satellites. tracking their positions, handling orbit adjustments, and sending updates and managing service quality. Together, these systems keep the constellation running smoothly and make sure data moves efficiently between space and the internet. So the user segment is what the end user actually interacts with, which mainly through the user terminals. These terminals automatically track satellites as they move quickly overhead and switch connections from one satellite to the next. Different types of terminals exist, including fixed home terminals and mobile ones for vehicles, aircraft, and ships. Because LEO satellites move so fast, constant handovers are required, and user terminals are designed to pick the best satellite at any moment to keep latency low and maintain a stable connection.
And after talking about the function and operations of the Leo network, now we are going to talk about comparison of Leo and the ground networks. Let's go to Amar.
Yes, my main idea was about the low Earth orbit satellites, also known as LEO. They are transforming global internet access, especially for isolated and rural areas where traditional networks cannot reach. The key point of this is for traditional networks to rely on fiber optic cables and wireless towers, which are expensive or impossible to install in remote locations. LEO satellites orbit only 500 to 2,000 kilometers above Earth, which is much closer than geostationary satellites, and their low altitude allows much faster signal travel, creating lower latency and enabling high-speed internet in places that previously had no connection. The performance and latency of Leo starts at approximately 25 to 40 ms, and the geostationary satellites go 600 plus ms. So the geostationary satellites are much slower, if that makes sense. And the fiber optic is 5 to 10 ms, which is pretty quick. And Leo offers near fiber speeds without needing physical cables, which saves like a lot of time if you were to set it up and stuff like that, which is pretty neat. The challenges and costs. The satellite lifespan of LEO lasts only 5 to 7 years, requiring constant replacement, and the space debris are thousands of satellites, raising concerns about orbital congestion and low-term environmental risks. And the weather sensitivity, due to like heavy rain and heavy snow, may reduce signal strength. But Adam goes on more about the challenges and of Leo, so I'm gonna pass it over to him now.
Even though the Leo systems and shows the strong performance benefit, and especially in remote regions, as Luke had mentioned, and the problem is they also face significant technical and environmental challenges. And Adam will bring us to the major limitations of Leo's constellations, from space debris to regulatory and sustainability issues.
This part is mainly just gonna be about the challenges that really LEO satellites encounter. A lot of people think that with these satellites, they're gonna become like a form of replacing fiber or cell towers, but that's really just not the case. They're really helpful, but they come with a lot of limits. So first off, here we have mainly like the technical stuff. They sit, like Luke said, they sit really low in orbit, so they have a small coverage area, and that's when you're gonna need thousands of them that work for the same company to be deployed to make that kind of web of network itself. And when you also have too many satellites, you get constant handoffs. Weather can play a role in coverage, and then you can also run into interference from different companies as well. So with all the effort of deploying thousands of them even, they can't match the bandwidth from fiber or cell towers. And then especially everybody being online at the same time also lowers your bandwidth. So then there's the environmental and the cost challenges. One of the big things that there is to talk about these satellites are good for about 5 to 7 years. Companies have to keep relaunching them, and then they kind of just turn into space junk. And it raises just, especially in low orbit, it raises percent chance of collisions. One thing is astronomers also talk about that they reflect light in a way that can mess up telescope images. Rocket launches to get these satellites into orbit also cause a lot of carbon emissions. And then on top of that, just the expense of this all. It's not cheap. And then even for consumers themselves, the cost of Starlink to get the equipment to run in your own home is $500. And then there's that $120 service fee every month. The people that it would be most helpful to, like getting into remote areas, they aren't even able to afford this service like Starlink. And then the last part is the regulatory side. First, there's the problem of if a company wants to um, provide service in a certain area, first they have to get government approval. Then they have to figure out what form of space use you can even use in low orbit, and then you have to get a pass from national security as well. So getting all those permissions can be really slow. It can also cause problems with politics, and then a lot of times you'll run into a situation where it's just impossible to get all those things together at once, leading it to not be available in areas that companies would like them to be. And so the last thing is for this to really work, you need that worldwide coordination, which I think a lot of us know it's pretty impossible to get the whole world to agree on anything these days. So you need the whole world to have worldwide coordination for these networks to really maximize their potential.
Adam brought up the major challenges and the limitations. It gives us a context for the technology's future impact. To close, Ryan will look at the broader and global and socioeconomic effects of LEO satellite networks and how they may reshape connectivity, development, and global communication.
And with LEO satellites, like everybody else mentioned, it helps everybody and it helps connect the world and faster with better connectivity. And so like it's been seen like it's pretty much a huge surge in usage around the world, which in turn a lot of people in lower economic status positions are finally able to use better internet and better connection, which is made to be much easier. And with the use of configuration and meticulous satellite interlinking and ground support, which allows for the LEOs to work fast and efficiently and provide high-speed networks across the globe. And the biggest benefit socioeconomically, like I mentioned earlier, is the ability to connect people across the entire globe. People who live in either Morocco or China or Brazil now have the ability to connect with each other and be able to interact with each other previously than previous years or previous lives before. And it also helps people with lower economic status to be able to catch up, quote unquote. Like historically, let's say an area or community has seen the best with either like coming into finances or building a better community around. Now they have the ability to, with better internet access, have easier access to school, healthcare, and better jobs, and so much more.
That's true. And from this together, all of these perspectives we have mentioned, from technical structure to global impact, shows how LEO satellite networks are not just an engineering system, but also a transformative step in worldwide communication. Here's some extra aspects about potential challenges. Our resources, they are written in the research paper, and if you are interested, please view our research paper document. And again, thank you for everybody to witness this presentation, and thank you for the patience and the time you guys have devoted. And we'll see you guys next time. Bye.